Well, we're going to do some antiderivative problems by exploiting Taylor polynomials. Two of these problems fall under the category of really impossible to do using elementary functions unless you are willing to use Taylor polynomials. And then one of these problems doesn't need a Taylor polynomial at all if you can remember the derivative. So let's get started. We're going to take the antiderivative, well, the indefinite integral from 0 to x of e to the t squared. And to get this started, remember that the Taylor polynomial for e to the x looks like this. And each place where I've left a little void here is where the x goes. So x and x and x. And the next term is 1 over 3 factorial, x cubed, etc. But I don't have in mind today to put x in there. I want to put t squared in there. And so that's how I'm going to start this problem. I'm going to go and replace e to the t squared with this Taylor polynomial. 1 plus, and I'll put t squared here. So that's just t squared. I'll put t squared here, and I'll have to square t squared and get t to the fourth. So that's 1 over 2 factorial t to the fourth. Put t squared here, and I'll have plus 1 over 3 factorial t to the 2 times 3 is 6 power. And then you can see the pattern developing here. Of course, the next term is 1 over 4 factorial t to the 8th power dot 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 dt. Okay, so now we can apply the fundamental theorem of calculus and term by term just take antiderivatives. And so that would look like this. Antiderivative of 1 is t. The antiderivative of t squared is 1/3 t cubed. The antiderivative of t to the fourth will go up to t to the fifth, so I'm going to have to divide by 5, as well as I have a factorial of 2 down here. And the next one looks like t to the 7th, so I'm going to have to divide by 7, and I have a 3 factorial as a divisor, and I guess we can do one more here. The next one ends up being 1 over 9 times 5 or 4 factorial t to the 9th, and we're going to evaluate that at x and 0. Well, I'm not going to put both of those in. I'm just going to put the x in, because having evaluated at x and then evaluated at 0, the subtraction would just subtract 0, right? Put 0 into all these terms and you get 0. So you really only need to put x in for this particular problem, and that looks like this. It's really just the same thing I have here, except everywhere there's a t, I have an x, and so forth, and so on. And that's good enough. Now we're supposed to write the sigma notation. This is a little bit challenging. The sigma notation looks like this. You have a choice of starting at n equals 0 or n equals 1, or I guess you could start at 2 if you wanted. I usually start at 0. And then I sometimes find it helpful to go back to these terms and write down the term index. If you're starting with 0, this is called the 0th term, and the first term, and the second term, and the third term, etc. Okay? Now, one of the things you're going to have is a fraction that has 2 divisors in it. One of the divisors is this 3 or this 5 or this 7. Notice these are moving by 2's, so that tells me I'm dividing by 2n. And yet if you plug 0 into, for example, the first term, 2 times 0 doesn't make 3. Likewise, if you plug 2 into this term, 2 times 2 doesn't make 5. It makes 4. So it's apparent that you have to add 1 here. And then the factorial is pretty easy, because this is 3 factorial, the next is 4 factorial. Those are just moving by 1. So you just put n factorial down here. And then we also said that the exponent up here matches the number in the that you're dividing by down here. So these are 5s, these are both 7s. That means that if this is 2n plus 1, this is 2n plus 1 also. And you should confirm for yourself that that is the correct sigma notation. Let's try another one here. Find an antiderivative of sine of x squared. Includes sigma notation. Well, just like the previous problem, I want to remind myself of what the power series for sine is. So sine's power series starts with x and subtracts 1 over 3 factorial x cubed, and then adds 1 over 5 factorial x to the 5th, like this, and then minus 1 over 7 factorial. Yeah, that's the pattern. X to the 7th. But the deal is, I want x squared everywhere that sine normally has x. So instead of x here, I'll put x squared, and that means all these have to be x squared in here also. So what do we get? We get x squared, x to the 6th, x to the 10th, x to the 14th, etc. So the antiderivative for sine of x squared then can be written as the antiderivative of this power series. So I have x squared, 1 over 3 factorial, x to the 6th, 1 over 5 factorial, x to the 10th. I'll put one more term in here, minus 1 over 7 factorial, x to the 14th, and dot, dot, dot. So now, just term by term, take an antiderivative using the inverse power rule. This becomes 1/3 x cubed. This becomes x to the 7th power. So down here where the 3 factorial is, you're also going to have a 7. Then we're back to plus. We'll raise this to the 11th power. You're going to have to divide by that 11. So this fraction will have an 11 and a 5 factorial in its divisor. This goes up to the 15th power, so you'll have to divide by 15. So down here in the divisor of this fraction, you'll have a 15 and a 7 factorial. And because it's an antiderivative, probably ought to put plus c in here, which I didn't need in the last problem, because in the last problem I was really doing a indefinite integral, and I put 0 in right at the point of evaluating with the x and the 0, and the 0 really didn't have any bearing because all these terms zeroed out. So plus c. Now I'll move that c to the front and I'll write down the sigma notation. So it's c plus the sum from n equals 0 to infinity. And since I started counting with 0, this is called the 0th term, not the first. This is the first term, this is the second term, the third term, etc. And what do we need? Well, we need a fraction that has 2 divisors. One of the divisors is the number that matches the exponent, the other is the factorial. We're also going to need to be able to turn on the positive and the negative, the plus and the minus, off and on. So a good way to do that is just to write -1 to the n power. And make sure that really works. Let's see, -1 to the 0 power, when I'm on my 0th term, is positive. On the first term, -1 to the 1st power is negative, so that's going to work. Now, how about this exponent up here and the divisor down there that match? Notice that they go 3 to 7 to 11 to 15. They're moving by 4s. So both here and here, you're going to need some kind of a 4n term. And then you can just adjust it to see what else you need. So when n equals 1, 4 times 1 is 4. You'll need 3 more to get to 7. When n equals 2, 4 times 2 is 8. You'll need 3 more to get to 11. So apparently it's 4n plus 3. And that's also the exponent. And finally, the factorial goes 1 factorial, 3 factorial, 5 factorial, 7. Those are moving by 2. You're going to need 2n plus 1 on the factorial. And we can check that against one of these, for example. Let's see. If n is 3, 2 times 3 is 6 plus 1 is 7. Yep. You could check it on another one down here. If n is 1, 2 times 1 is 2 plus 1 is 3. So we got the factorial right. And there is your power series for the antiderivative of the sine of x squared. We're going to do one more here. Now this one is not impossible to do without Taylor series, and I'll make a comment about that right near the end. But I'm going to use the Taylor series for it because I like these things. And the Taylor series that I have in mind for this one is 1 over 1 minus x is the geometric series, which looks like 1 plus x squared plus x cubed, dot, dot, dot. But when you look down here, you don't see a minus sign, and you don't see x, you see x squared. So remember, 1 over 1 plus x squared is the same thing as 1 over 1 minus negative x squared. And that is what you're going to put into all these voids. So you have negative x squared here, negative x squared here, negative x squared here, and negative x squared here. And you'll end up with all even exponents of 2, 4, 6, and 8, and so forth. And this thing is going to alternate because this negative sign is not affected by that square. It survives. This negative sign is affected by this square. This negative sign is not affected by this x squared because the squared only applies to the x. And the cube preserves the minus. So we'll have an alternating power series, and we'll be finding an antiderivative of 1 minus x squared plus x to the 4th minus x cubed. You can see what comes next. Yes, it had to be a plus, and it would be x to the 8th. And dx. And then all you have to do is use the inverse power rule, find an antiderivative term by term. So this is going to be x minus, raise it up to the 3rd power, 1/3 x cubed, raise it up to a 5th power, you have 1/5 x to the 5th, minus up to a 7th power, 1/7 x to the 7th, plus 1/9 x to the 9th, etc. And depending upon where this originated, you want to write plus c on the end of this. You may recognize this power series, or maybe you don't. A few of you may have recognized this as being the derivative of arctangent. We could have saved ourselves a lot of trouble if we'd have just known, oh, that's already a derivative. That's the derivative of arctangent. So the antiderivative of this thing that's already a derivative should just be arctangent. And indeed, this is probably the best way to come up with the power series, which turns out to be a Maclaurin series of arctangent. And that's all I have for today. My name's Eric. Hope you enjoyed this. Have a good day.